Now we continue with the lesson 5, emulsions. We will look into the definition, the thermodynamic properties, and the practical applications of emulsions. It is a topic central to both industrial chemistry and our daily life. What is an emulsion? By definition, emulsion is a colloidal dispersion, which consists of two or more liquids that are either completely or partially immiscible. In this system, one liquid known as the dispersed phase exists as a tiny droplets suspended within the other liquid known as the continuous phase. In a system consists of oil phase and water phase, the boundary where these two liquids meet is called the interface, as this line as the boundary. It is important to understand that emulsions are unstable systems. So naturally, those dispersed droplets in the continuous phase will want to agglomerate or coalesce and eventually phase separate into their original distinct phases. The characteristic of emulsions. A key takeaway is that emulsions do not form spontaneously. To create emulsion, you must provide energy input via shaking, stirring, or using a high-tech homogenizers. Because they are thermodynamically unstable, the system will always try to revert to its stable state, where involve the complete phase separations. So to minimize the contact between the hydrophobic and also the hydrophilic molecules, that is the reason why they want to separate back to their initial state. Emulsion formation. When we create an emulsion, we drastically increase the surface area of the dispersed phase. For example, if you take 1 ml of the mineral oil and disperse into the droplets with the size of 0.01 micrometer as the diameter in 1 ml of water, then the total surface area increase will become 600 meters square, which by forming the droplets of oil in the water phase, the surface area of the system increases to 600 meters square, which is a size greater than a basketball court. The smaller the droplets form, the larger the total interfacial area becomes. This shows the difference between the size of the droplets. If we have 20 ml of oil and they form 1 centimeter radius droplets, so each of them will have the volume of 5.5 ml and the surface area will be 12.5 centimeter cube, whereby this 20 ml of the oil can form about 3.6 droplets with the total surface area 45.5 centimeter cube. With the same volume of the oil and dispersed in the water, it forms 0.1 centimeter radius droplets, which is 10 times smaller than the size in this image here. So the total surface area that can be up to 625 centimeter cube. This massive increase in the area is why this system requires so much energy to maintain. If they form the smaller droplet size like the dispersed phase in the emulsion. The thermodynamics of this process are controlled by the equations of delta G equals to gamma, which is the surface tension, multiplied the change of the surface area minus the temperature of the system, multiply the change of the entropy, delta S. So delta S measures the disorder in the system. As we reduce the size of the oil phase and increase the number of droplets, the disorder increases, so delta S will be a positive value, which actually contributes slightly to the stability of the system. we need to introduce energy into the system, and this energy is the enthalpy. So it can be considered as delta U at constant volume, where delta U is the internal energy change of the system, while delta U equals to the amount of heat released plus the work required to expand the interfacial area, delta W. The work required to expand the interfacial area, delta W, is the product of interfacial tension, gamma, multiplied the change in the area. Because both of these values are typically large, this produces a large positive interfacial energy term. Because the entropy is relatively small compared to the energy that we need to introduce to the system, so the total Gibbs free energy remains greater than zero. This leads to a thermodynamic instability and making the emulsion prone to coalescence, which is the destabilizations of the emulsion. While if we want to produce a system that is stable, then we have to make this term to be negative. So in order to the delta G to be negative, one of the way is if the interfacial tension is approaching zero. If we can reduce the interfacial tension to zero, then we get a truly stable system. However, in most cases, we add surface active substances to improve the kinetic stability. Without this help, the system requires significant external energy. But if the interfacial tension is extremely low, then the spontaneous emulsification can occur. Can be classified according to their character. One of it is based on the dispersed phase. According to the Bancroft rules, emulsion types depends on the nature of the emulsifying agent rather than depends on the relative proportions of the oil or water presence or the methodology of the preparing emulsion. How do we know which liquid becomes the continuous phase? We use Bancroft rule. This rule states that the phase in which the emulsifier is more soluble will become the continuous phase. In oil in water emulsions, emulsifying agents are more soluble in water than in oil. While in the water in oil emulsions, the emulsifying agents are more soluble in oil than in water. Oil in water emulsions include the example of milk, mayonnaise, soluble paint, and also the body lotions. In these oil in water emulsions, the oil droplets are dispersed in the continuous phase of aqueous or water. The surfactant molecule will arrange in the normal micelle manner where the tail is pointed to the hydrophobic region consists of oil, and the head group of the surfactant will be pointed towards the continuous phase. On the other hand, water in oil emulsions such as butter or certain skin cream, it has the continuous phase as the oil phase, while the dispersed phase are water droplets. So the surfactant will arrange in the manner as in the reverse micelle. Figure shows the orientation of surfactant twin and span molecules at the interface between oil and water. So we can see that the hydrocarbon tail, they are pointing towards the oil phase, for the head group, they are facing the water phase. The TEM images here shows the sample from mayonnaise with the oil droplets dispersed in the aqueous system. So usually we use the egg to bind with the oil and also the vinegar in the formations of mayonnaise. The egg yolk consists of lecithin, which is a kind of a phospholipid or the surfactant that can be surrounding the oil droplets so that the oil can be dispersed in the aqueous system. So all these droplets is corresponding to the oil phase. Other than the oil in water type emulsion or the water in oil type emulsion, there are also some multiple emulsions. Multiple emulsions are the emulsion system in which the dispersed phase contains more droplets that have the same phase composition as the external phase. So you will have the water in oil in water emulsion. Similarly, there are also the oil in water in the oil type of emulsion. So there are the emulsion more than two phases. Also characterize the emulsions through the size of the liquid droplets or the dispersed phase. In general, if the size is ranged between 0.2 mm to 50 mm, then it is categorized as the macroemulsions. The macroemulsions will appear as an opaque appearance, and they require a very high energy input in order to produce the emulsion. If the size of these emulsions is in the range of 20 nanometer to 200 nanometer, then the appearance is transparent because the droplet size is smaller than 25% of the visible wavelength. So they don't scatter the light. And they require very high surfactant concentrations in order to produce this type of microemulsions so that it can reduce the interfacial tensions between the oil and water to become very low and close to zero. Emulsions are rarely uniform. A polydispersed emulsion has inconsistent droplet size and shapes, while a monodispersed emulsion has uniform droplets. Generally, a narrower size distribution leads to a more stable system. So, a system that has a polydispersed droplet size, the polydispersity index is a very large value, while a monodispersed system usually will result in a polydispersity index that is very low, for example, around 0.2 or 0.1. By referring to the size distributions for the different type of emulsions given here, so can you estimate which one is the most stable emulsion? Emulsion 3 is the answer. Why? Because it has the narrow size distributions, while emulsion 1 and 5 has the more polydispersed emulsion compared to emulsion 3. Therefore, emulsion 3 is the most stable system. Emulsifier and stabilizer. Emulsifiers are specialized compounds that primarily facilitate the formations of an emulsion. They work by lowering the oil-water interfacial tension. If you recall our earlier discussion on the thermodynamics, reducing the interfacial tension lowers the total energy required to create those billions of tiny droplets which can disperse in the continuous phase. While stabilizer get the jobs to start to stabilize the system, where they keep the system together over a longer period of time. Unlike emulsifiers, stabilizers are generally not surface active, or only slightly so, meaning they do not necessarily lower the interfacial tension. Instead, they impart long-term stability by restricting the interfacial interactions. We can classify emulsifier and stabilizer according to the different types of the materials. The first one is the adsorbed ions or non-surface active salts. So this group consists of simple ions or salts that are not surface active in the traditional sense. These substances have little effect on the interfacial tension and they do not make it easier to create the emulsion. Instead, they function by absorbing on the surface of the droplets to provide an electrostatic barrier. You just imagine that each oil droplet in the water getting a coat of negative or positively charges. Because light charges repel each other, two droplets that are about to collide or merge will instead push each other away due to this electrical repulsion. The second type is called the colloidal SAW, which involves the use of very fine solid particles. So we call this solid particle as the colloidal SAW. Like the ions mentioned above, these solid particles have little effect on the interfacial tension and do little to facilitate the initial emulsification process. They do not efficient in the forming of this emulsion, so they don't help in the formations of the emulsion. Their effectiveness as stabilizers depends heavily on the size and also the particles and the interfacial interactions between the solid surface and the two liquid phases. So this solid particle will just sit right at the boundary between the oil and also the water, acting like a physical fence around the droplets. So this is also called a Pickering emulsion. For the droplets to merge, they would have to physically display this solid particle, which require a great deal of force. The next type is polymer molecules, which involve the steric stabilizations or the electrostatic stabilizations provided by this polymer molecule to prevent close approaching between the dispersed phase. In addition to that, the polymer molecules also increase the viscosity of the medium, so it will prevent the fast aggregations between the droplets. The last group is the surfactant. Surfactant can effective and significantly lower the interfacial tension of the system. They reduce the energy barrier required to create and maintain the interface. They impart stability to the entire system. Surfactants have a dual nature, as what we have already learned, and this allowed them to sit exactly at the boundary, acting as a bridge between the two immiscible liquids. Because they reduce the interfacial tension so much, the system doesn't have to work as hard to keep the droplets small and dispersed. Emulsifier. Because of their amphiphilic nature, it absorbs at the interface between the oil and water to form the interfacial film, and this creates repulsive droplet-droplet interactions at the droplet surface and cause reductions in the interfacial tension. The reduction in the interfacial tension through additions of emulsifier allow the emulsion formations with considerably less energy input. Therefore, we can ensure extensive mixing of oil and water. The example of emulsifier include the phospholipid, proteins, and some of the fatty acids. Emulsifiers are present in food. The two commonly found emulsifiers in food are twin and span. This emulsifier not only concentrate at the two immiscible phases, it can also be found in the interface between air and solid or air and liquid, such as the presence of gas bubble in the foam, or it will also be present at the interface of solid and liquid, such as ice crystal in the ice cream or sugar crystal in the chocolate. So emulsifiers, their presence will influence the consistency the viscosity and the texture of many multi-phase food systems. Ice cream is an example of emulsion where it is both a foam as well as emulsion. The ingredients of ice cream includes milk fat with the compositions around 10 to 16%. Milk fat is used to increase the richness of the ice cream flavor to produce a smooth texture and give the body of the ice cream. Then we have the next ingredients, which are the milk solid not fat, such as proteins that are present in the milk like casein, whey protein, lactose, and also some mineral salts to improve the body and texture through the emulsification and water holding capacity. Then next we have the sweetener such as the sucrose, corn syrup with a percentage like between 12 to 16%. And lastly, we need to have the stabilizer or the emulsifier with a very small percentage between 0.2 to 0.5%. An emulsion is formed as the milk or the cream is dispersed in the ice or water as well. So basically we must have the water to presence as a larger component, which is about 50%. So basically the molecules of the fat are suspended in water, sugar, ice structure along with some air bubble. What does the ice cream looks like? If we take some sample of the ice cream and view under the cryo scanning electron microscope, this is the feature of the micrograph that introduce the cross sections of the frozen ice cream. So it will consist of 4 phases. And these 4 microscopic phases include the frozen ice, which is the ice crystal labeled as a C here. So these are the ice structure. And then we also have some air bubble to present as denoted with the symbol of A here, which is the air are trapped in the ice cream or the emulsions. Therefore, we call it as the foam. And then we also have the fat bodies, which is the fat droplets, F, and the unfrozen phases, those like in the S phase. So this is how the both air, ice crystal, and also the fat droplets present in the ice cream. As mentioned earlier, the milk fat in the milk will exist in a tiny globules that have been formed by the process of homogenization. So the air in the ice cream does not mix with the other substances, but they will form a small bubbles in the bulk. And the properties of these colloids and therefore the ice cream depends on the interface that forms between the 2 phases. Emulsifier and proteins are surface active molecules that act to keep the 2 liquids, which are the fat and also the water, that do not mix naturally from separating. So we may expect that emulsifiers are added to ice cream to prevent the milk fat and water from separating. Well, in the presence of the emulsifier will be replacing the organization at the interface between the fat and also the water. And this image here, it shows the participations of the emulsifier at the interface. If there is no emulsifier presence, then the appearance is something looks like here, where the fat globules will be stabilized in the water through the adsorption of the protein molecules such as the casein. Well, it is the milk protein that emulsifies an ice cream mix and not the added emulsifier that is required. So in fact, we do not need to have the emulsifier in the ice cream to stabilize the fat emulsion due to the excess of protein and other amphiphilic molecules is already sufficient to stabilize the interface. But why do we need to add in the emulsifier? Why emulsifiers used in the ice cream? Since we already have the casein that acts to emulsify the ice cream mix by preventing the water and fat from separating. By adding the emulsifiers, it will reduce the interfacial tension between the serum and the lipid phases in this mixture. So it is more favorable for the emulsifier rather than the casein to adsorb to the fat surface at homogenization, because this will lead to a lowering of the net free energy of the system. And this reduction in the amount of casein on the fat surface, however, it produces an emulsion that is less stable when the mixture is subjected to the process of whipping. And this is due to the emulsifier molecules are loosely anchored to the fat globule and thus are swept off during the process of agitation, and hence removing the protections of the globule, while the fat emulsion begins to partially break down and the fat globules begin to flocculate or destabilize. And next question is, usually we introduce the emulsifier or stabilizer is to stabilize the emulsion, while in this case, in the formations of the ice cream, although the casein is already sufficient to form the stable system, but emulsifiers still added in. So what actually is the role of the emulsifier here is to promote the process of destabilization. And why do we need to have the partial coalescence or the stabilizations to occur? Usually we want a stable emulsion, but in this case we are trying to promote the process of destabilizations, which is opposite to our general needs. This partial coalescence or the destabilizations is very important because it contributes significantly to the smooth and the creamy texture of the ice cream. How? During the process of the churning, air bubbles are being beaten into the mixture. They are stabilized by this partial coalesced fat. So when we beat in the air will be trapped in between the fat, whereby the surface of the air bubble in the ice cream are covered by the milk proteins, and partially they will coalesce to form the fat globules. If the emulsifier were not added, the fat globules would have so much ability to resist this coalescing. Due to the protein being adsorbed to the fat globule, that the air bubbles would not be properly stabilized and the ice cream would not have the same smooth texture. So, emulsifiers are added to ice cream to promote the partial coalescence of fat particles, so that fat particles form clusters and clumping into an ice cream mix to trap the air inside when it is churned in the machine, and it will result in a much more smooth texture. While protein, which is the casein in the milk, is stabilize the fat emulsion in an ice cream mix, emulsifiers are added to ice cream to reduce the stability of this emulsion and encourage some of the fat globules to come together or partially coalesce to improve the texture of the ice cream. Since there are different types of emulsion such as water in oil, oil in water, or multiple emulsions, so how are we going to identify the type of the emulsions? Based on the Bancroft rules, many emulsions properties are controlled by the properties of the continuous phase. The texture of the emulsion frequently reflects that of the external phase. The oil in water emulsions usually feel watery or creamy. Water in oil emulsion will feel oily or greasy. So this distinction becomes less evident as the emulsion viscosity increases. Another test can be done is through the dye test. Water-soluble dye will dissolve in the aqueous phase, while oil-soluble dye will dissolve in the oil phase. Methylene blue or brilliant blue are a kind of water-soluble dye. So this dye, when you sprinkle onto the emulsions of oil in water, the dye will dissolve. In contrast, if you sprinkle this methylene blue in the water in oil emulsion, the particles of the dye will lie in clump and just stay on the surface. This test was conducted by a student. So she used a Sudan 4, and first of all, she would test what type of properties is this dye. Therefore, she sprinkled the Sudan in oil and also in water. So this is the outcome when the Sudan is present in the oil phase. On the other hand, when you have the Sudan in the water phase. After that, she conducted a test with using another type of the dye, which is the crystal violet. So she did the same thing, sprinkle the crystal violet in oil phase and also water phase. And the result is shown here, whereby in the oil phase, it just appears as a transparent with some powder of the crystal violet. On the other hand, in water, we can see that the crystal violet is dissolved and dispersed in water. So it shows that crystal violet is a kind of water-soluble dye. Next, she continued to test the emulsion that she has prepared by using both Sudan red and also the crystal violet. So she just dropped a drop of the dye on the emulsion and she observed the changes of the emulsion. So in the Sudan red, the dye just remained as a droplets without spreading the whole emulsions. On the other hand, for the crystal violet, she can see that the crystal violet can be very good dispersed in the emulsion. Therefore, she makes the conclusions that the emulsion that she has prepared is a kind of oil in water type emulsion. When you look the system of the emulsion with dye under the microscope, then the appearance of the oil-soluble dye emulsions will be something similar to here. With oil in water emulsions, the oil droplets will consist of the dye. For water in oil emulsion, then the continuous phase will be filled with the dye. If you have another type of the emulsion, water-soluble dye was used, then you will see that if the continuous phase is water, then it will be able to dissolve the water-soluble dye. While on the other hand, if you have the water in oil emulsion, the water-soluble dye will just trap in the water droplets, which is dispersed in the oil phase. Dilution test is another alternative to determine the type of the emulsion. Dilution test is based on the solubility of the external phase of the emulsion. or an emulsion readily mixed with a liquid that is miscible with the continuous phase. Oil in water emulsion can be diluted with water, while water in oil emulsion can be diluted in oil. So if you have a test tube and fill with some emulsion, after that you fill in a few drops of the water. If the water distribute uniformly, then it tells us that the emulsion that we have is a kind of water in oil emulsion. If the water that we added in separated as a layer, then it shows us that the emulsion that we have is a kind of water in oil type emulsion, where the continuous phase is oil, so it cannot simply just mix with the water that we further added. This figure illustrates in more detail upon the additions of water into the emulsion. Two different types of emulsion, oil in water, water in oil emulsion. When water was added in, for oil in water emulsions, there is no changes. If we add in the diluted oil into the water in oil emulsion, there will also be no changes in the phase. If we further add in oil into the oil in water emulsion, then the oil will just remain on top as a separated phase. Similarly, if we add in water into the water in oil emulsion, the water will also be remain as a separating phases. So we can try to test the type of the emulsion by using the dilution method. Next is the conductivity test. The basic principle of this test is that water is a good conductor of electricity, where oil is a non-conductor. So you can actually tell the difference between the two emulsions by measuring the electrical conductivity of the emulsion. So usually the oil in water emulsion will have a higher value of conductivity compared to water in oil emulsion. We also can perform the cobalt chloride test. When a filter paper soaked in the cobalt chloride solutions is dipped into an emulsion and then dried, it turns from blue to pink, which indicate that the emulsion is a kind of oil in water type emulsion.